So chapter 2 is all about graphs. So now let's talk about graphs of equations in two variables. And we'll also be talking about intercepts and symmetry. So we're going to first remember how to graph equations by plotting points. And it can be really helpful to go back to this idea and remind yourself that whenever we're graphing equations, we're actually graphing a bunch of points really close together. Then we're going to look at finding intercepts from a graph, and then find intercepts from an equation. Then we're going to learn how to test an equation for symmetry. And we have three different kinds of symmetry that we'll look for with respect to the x-axis, the y-axis, and the origin. And then we also need to know how to graph key equations that some people call a library of functions or parent functions, parent graphs. Okay, so first, remember about graphing equations by points. If you have an equation with two variables, so look at how this is different than what we've been doing in chapter 1, where we only had one variable. Now we have two variables. And we say that values of the variables that make the equations true, the word we use is satisfy. They satisfy the equation, or they are solutions of the equation. So when we have two variables, there are lots of solutions. So if we have an equation like y equals 2x plus 5, 0 for x, and y equals 5 is one solution of many. So there are lots and lots and lots of solutions, and the set of solutions we can draw in a picture, and so that's what the graph is. So the graph of an equation in two variables, x and y, is the set of points that satisfy or make true the equation that you're looking at. Okay, so this is a really important concept that you can go back and forth between equations and graphs. So the equation is something algebraic, and the graph is a picture of that. So we're going to use an equation to determine whether a point is on the graph of an equation. So we're deciding which of these points are on the graph of this equation. Well, we will learn about equations like this later and learn that this is actually the equation of an ellipse. But when we go to check and see if a point is on the graph, we say, well, let's plug in 0 for x and 1 for y. And we're asking, is this true? Sure enough, we get 4 equals 4. So the point 0, 1 is a point on the graph. So it's important that you know what you're testing for and what your conclusion is. So if we graph an equation by plotting points, you might have to do a lot of them to see what the shape is. So you'll see that a lot of the other things we do in this chapter will be so that we don't have to do it by plotting points. But sometimes it can give you an idea of what the graph looks like if you plot a few key points. So if you're given an equation in two variables like x squared plus y equals 5. Notice this one is not linear because the x is squared. So you can either choose values of x and solve for y, or you can choose values of y and solve for x. Typically, we choose values of x and solve for y because x is what's called the independent variable. And usually it's the one that is changing, and then the y is depending on the x. And so that's why we set it up that way. So these two examples, it might be easier to choose values of x in one case and find y's, or choose values of y and find x. So either one is fine. And then you plot them and connect with a smooth curve. In this class, we're all smooth curves. We're not doing anything with jumps or out of the ordinary things. So you pick a few values of x. Don't forget to do some negative values. So if x is -2, you get that y is 1. If x is -1, you get that y is 4. If x is 0, y is 5. Oh, we're noticing there is some symmetry here. So then you would plot these points. You'd say when x is -2, y is 1. When x is -1, y is 4. When x is 0, y is 5. And so on. And we can see the shape of the graph. I'm very picky about labeling your axes, so just get in the habit of doing it all the time. And we'll look at this problem in class together. Okay, so now we're going to look at finding intercepts from the graph. And intercepts are always important points on a graph. If the graph is showing you a picture, telling you a story about something that's going on, intercepts are always some important thing that's going on. So if a graph crosses or touches a coordinate axis, the x-axis or the y-axis, we call the point where that happens an intercept. So graphs can have x-intercepts and or y-intercepts, or they can have no intercepts. If you have a graph of a circle that's up here in quadrant 1, it has no intercepts at all. So the point where a graph crosses or touches the x-axis is called an x-intercept, and where you touch or cross the y-axis is a y-intercept. So graphically, this is very easy to do. So if somebody says find them graphically, it means from a picture. And so we can see the intercepts here and write that the coordinates are -2, 0, 0, -3, and 2, 0. So if somebody asks you, what are the x-intercepts? You would say -2, 0, and 0, and 2, 0. And the y-intercept is 0, -3. So sometimes if all you're asked about is x-intercepts, you can say 2 and -2 if the context is clear. If the context is not clear, then you need 2 coordinates to be clear. So this is a fine point that's brought out in your book. If the type of intercept is not specified, you need to report as an ordered pair. But if it is specified, then you can just say what the coordinate is. Okay, so the third objective is about finding intercepts from an equation. So that's going to involve some algebra. So this is find the intercepts algebraically. So from a picture is graphically, and using algebra is algebraically. So think about what the y-coordinate of an x-intercept has to be. And it has to be 0, right? So the y-coordinate of an x-intercept is 0. So every x-intercept is going to look something like c, 0. And now think about the x-coordinate of the y-intercept. Make a picture in your mind, y-intercept. Oh, the x-coordinate has to be 0. So that means every y-intercept is going to look like 0, d. So using that information, the way you find when that happens, you can find intercepts from an equation by solving for x when y is 0. So you're setting up this situation. You're saying, well, put that y is 0 and find x-intercepts. And then if I put 0 in for x and solve, I'm going to find y-intercepts. Make sure that's very clear to you. So we're going to work on this one in class and list all these intercepts. And objective 4 is about testing for symmetry. So if a graph has symmetry and we can detect it algebraically, it can simplify drawing the graph. So symmetry is when something has a shape that's repeated. So you can see that this shape has symmetry about this axis, where if I fold it over this axis, it matches up. It also has symmetry about this axis, where if I fold it over this axis, it matches up. So we're going to look at symmetry with respect to the x-axis, the y-axis, and the origin. Those are the three kinds of symmetry that frequently occur. And there's other kinds, but those are the three that we're going to focus on. So a graph is said to be symmetric with respect to the x-axis if for every point xy on the graph, the point x negative y is also on the graph. And this is a picture to show why that happens. Well, that's the picture. And so we can see that algebraically, we replace y with negative y and see if the x values match. So if we want to test for symmetry with respect to the x-axis, we replace y with negative y and see if we get the same thing once we simplify. So we have symmetry, and then we write with respect to, so you don't have to keep writing that out, with respect to the x-axis. So if you keep thinking about this picture, this will help you think of what to do with the algebra. And then we'll draw a graph of this using Desmos. So a graph is said to be symmetric with respect to the y-axis if for every point xy on the original graph, the point negative xy is also on the graph. So algebraically, we're going to replace x with negative x and see if we get the same y value. So you can see where if the x is squared, of course, when I square negative x, I get the exact same thing as when I square x. So we have symmetry with respect to the y-axis. Okay, and then the third kind is symmetric to the origin. And then every point xy on the graph has to have the point negative x, negative y, also on the graph. So you can probably see that we're going to replace x with negative x and replace y with negative y to see if everything comes out exactly the same. And we'll test this one together. Okay, so this is a little recap of the tests for symmetry from your book. And then objective 5, we're going to talk about these equations that you should be able to make graphs of quickly, and we'll work on those in class.